You'll notice that this is a relatively short past paper tutorial, and that's because there's not that many questions that directly relate to fission in past paper questions. So just enjoy the fact that this is a relatively easy and relatively short topic. We'll go through 9 questions just now. Question 1. What is the function of the moderator in the thermal nuclear fission reactor? The moderator is the liquid that surrounds the fuel rods, and that liquid has to absorb kinetic energy. By absorbing kinetic energy, you're decreasing the kinetic energy of the neutrons. The answer is A. Question 2. One possible fission reaction of uranium-235 is, and it's given here, state what is meant by binding energy of a nucleus. This is a definition that you just need to know. There's 2 ways of memorising this definition. The first way is looking at when we're separating the nucleus, so energy required to completely separate the nucleons. And the second way to memorise it is looking at the energy released when it's formed. So the second definition is the energy released when a nucleus is formed. And we'll put from its constituent parts. It's up to you which one you tend to memorise. I go with this one usually because it's easier and quicker. A2. Outline why quantities such as atomic mass and nuclear binding energy are often expressed in non-SI units. The SI units for mass is kilograms, and the SI units for energy, well, a derived SI unit for energy is joules. If we were to give the mass of a proton is 1.66 something times 10 to the minus 27 kilograms, it's tiny and it's not appropriate. Same with energy. We're looking at 10 to the minus 19 joules and so on. It doesn't really work for us. So it's better for us to use these derived non-SI units to make it easier. So the answer here is the values in SI units would be very small. A3. Show that the energy released in the reaction is about 180 mega-electron volts. Let's go back up to the data. There's energy released in this reaction, and the energy released is due to the mass defect of these. Subtract that. So let's do it. 140 times 8.29 mega-electron volts plus 94 times 8.59 minus 235 times 7.59. It gives us an answer of 184 mega-electron volts. Let's take that down. 184 mega-electron volts is equivalent to or nearly 180 mega-electron volts. A nuclear power station uses U-235 as fuel. Assume that every fission reaction of U-235 gives rise to 180 mega-electron volts of energy. Estimate in joules per kilogram the specific energy of U-235. So how much energy is given out in 1 kilogram? The first thing we'll have to do is find out how many isotopes of U-235 are in 1 kilogram. Let's find out the mass in kilograms of one isotope of U-235. There's 235 nucleons times the mass in kilograms of one nucleon. Now, I know what you're about to say here. You're about to say that how do you know that is the mass of one nucleon? Because the masses of protons and nucleons are slightly different. But it does say estimate, and both the mass of a nucleus and the mass of a proton start with 166. So I'm happy with using 1.66 times 10 to the minus 27 as my value of the mass of a nucleon in kilograms. So the mass of one isotope of U-235 in kilograms is 3.9 times 10 to the minus 25 kilograms. How many of them are in 1 kilogram? 1 divided by that number. There are 2.56 times 10 to the 24 uranium isotopes in 1 kilogram. Each of those uranium isotopes gives out 180 mega electron volts of energy. So the total energy given out in 1 kilogram is 2.56 times 10 to the 24 times 180 mega electron volts. But they want it in joules. So instead of doing it times 180, let's put in the appropriate calculation to turn it into joules. If we pop that all into our calculator, that gives us an answer of 7.38 times 10 to the 13 joules, which is our final answer. Oh, actually, let's give it to two significant figures. There we go. B2. The power station has a useful power output of 1.2 gigawatts and an efficiency of 36%. Determine the mass of uranium-235 that undergoes fission in 1 day. First of all, let's address the idea of efficiency. The useful output is 1.2 gigawatts, which is 1.2 times 10 to the 9 watts. But that's 36% of what was actually used. So to find the amount of energy actually used, we divide that by 36%, and that tells us that 3.3 recurring times 10 to the 9 watts was actually used to get that useful power output. And that's in watts, which is joules per second, and we're looking at per day. So we want to work out how many joules per day we have. So we take 3.3 recurring times 10 to the 9 times 24 hours times 60 times 60. And that gives us how many joules per day. We're looking at 2.88 times 10 to the 14 joules per day is required from that uranium to generate the power we need. And those joules are coming from the uranium fission reactions. And we know that each uranium fission reaction has 7.4 times 10 to the 13 joules. So to find the number of uraniums that are required, we need to do 2.88 times 10 to the 14 divided by 7.4 times 10 to the 13. And that gives us 3.891 kilograms. I will give that two significant figures, 3.9 kilograms. A sample of waste produced by the reactor contains 1 kilogram of strontium-94. Strontium-94 is radioactive and undergoes beta- decay into a daughter nucleoid X. The reaction for this decay is C1, write down the proton number of nucleoid X. Our beta particle has the following proton and nucleon numbers, and the left-hand side has to balance the right-hand side. So we have to have 39 protons minus 1 to equal 38. The proton number is 39. The graph shows the variation with time of the mass of strontium-94 remaining in the sample. State the half-life of strontium-94. We start off with 1 kilogram. The half-life is related to 2.5. Bring that down. The half-life is 75 seconds. C3. Calculate the mass of strontium-94 remaining in the sample after 10 minutes. How many half-lives are there in 10 minutes? 10 minutes is equal to 600 seconds. Divide that by 75. Tells us that there are 8 half-lives. So we go from 1 down to a half. That's 1 half-life. 2 half-lives. Bear with me. And finally, the final half-life takes us down to 1 over 256. That's the 8th half-life. So there's 1/256 of a kilogram left. That gives us an answer of 3.9 times 10 to the minus 3 kilograms. Question 3. What part of a nuclear power station is principally responsible for increasing the chance that a neutron will cause fission? We have to assume that the neutron's already out there. And if the neutron's already out there, it needs to be slow to cause fission. Slowing a neutron down is the role of the moderator. So the answer is A. Question 4. A neutron collides head-on with a stationary atom in the moderator of a nuclear power station. The kinetic energy of the neutron changes as a result. There is also a change in the probability that this neutron can cause nuclear fission. What are these changes? We need to reduce the kinetic energy to cause fission. So we need to change the kinetic energy by decreasing it. It's got to be B or D. by reducing the kinetic energy, that increases the chance that it will cause nuclear fission. So we increase. The answer is B. Question 5. During a nuclear fission of nucleus X into nucleus Y and nucleus Z, energy is released. The binding energies per nucleon of X, Y and Z are given by these terms. What is true about the binding energy per nucleon of X, Y and Z? X is an unstable nucleus. It's very large and it decays into Y and Z. They are more stable. They're not completely stable because they still are radioactive, but they're more stable than X. That means that the binding energy of Y is greater than the binding energy of X, and the binding energy of Z is greater than the binding energy of X. Let's see if we can use that information to answer the question. Oh, here we are, straight off A. 5A is the answer. Question 6. What are the principal roles of a moderator and a control rod in the thermal nuclear reactor? The control rod absorbs neutrons, and that controls the chain reaction. And the moderator slows neutrons down or absorbs kinetic energy. Let's look at moderator first. The role of the moderator reduces the kinetic energy, so it's C or D. The role of the control rod absorbs the neutrons, which means it maintains a constant rate of reaction. It doesn't absorb energy. The answer is C. Question 7. A nuclear reactor contains atoms that are used for moderation and atoms that are used for control. What are the ideal properties of the moderator atoms and the control atoms in terms of neutron absorption? The moderator atoms has to slow down the neutrons, not absorb them. So we don't want a neutron absorber for a moderator. We want to be a poor absorber of neutrons. The control atoms have to absorb neutrons to keep the reaction right. So it has to be a good absorber of neutrons. The answer is B. Question 8. What is the function of control rods in a nuclear power plant? It's to absorb neutrons, to regulate the reaction rate. D. Question 9. The Sankey diagram shows the energy transfers in a nuclear power station. Electrical power output of the power station is 1,000 megawatts. What is the thermal power loss in the heat exchanger? This is a trick question because the thermal power loss in the heat exchanger is equal to the power output of the power station because all of the thermal energy is lost. The answer is B. Trick question there. And that brings us to the end of the fission past paper questions. I hope you found that they're relatively straightforward.